Good day, guys. We are looking at a few more problems on theorems of geometry in maths level 4. So here we've got a circle with P, Q, R, S on the circumference. Then PR is the diameter. That's what I've picked up. That also means there is a radius, OR and OP. Then I see my tangent, MRT. O is the center. I'm just trying to pick up the information that I see in the equation. Then S2 is 63, R3 is 37, I clearly written there. Then I see a cyclic quad, PQRS. It's a four-sided figure in the circle with the four corners touching the circle. Then I see some chords like QR, SR, PS, even QS, they are chords. And even see I'm seeing triangles just to make sure that if I get stuck, I will see where I can go to pick theorems that will help me out. So, our beginning point is to calculate R1. If I go back to my diagram, you see that R1 is an angle between the tangent MRT and the chord QR. So that immediately shows to me that I need help from the tan chord theorem. So the tan chord theorem says that angle between tangent and chord must be equal to an angle in the alternate segment. So with the presence of the chord, that's the minor segment, the alternate will be the big one. But you must use that chord to create a triangle that takes you to the circumference. And if I do that, it takes me to S2, which is 63. So here, I will say R1 is equal to S2, which is equal to 63 degrees. And I'm using my tan chord theorem. So that is how I get my R1. So to be on the safe side, I can just go and put 63 there, so that in case I'm struggling, that one might help me to take me to the next stage. So let's go to the B part. We need R4, our next angle. If I go back to my diagram, my R4 is again an angle between the tangent MRT and another chord SR. So if I want to use tan chord theorem, I must use that chord SR to create a triangle that takes me to the circumference. So that triangle takes me to Q2. Unfortunately, I don't know Q2, so it will be difficult to calculate R4 using the tan chord theorem. But one nice thing here is that I've got a diameter. That diameter is also containing the radius, and you can see that the angle between the radius and the tangent must always be a right angle. So that therefore means R3 and R4 must sum up to 1 to 90, because the angle between the diameter, between the radius and the tangent, which is a right angle. So my R3 plus R4 should be equal to 90. I just say radius is perpendicular to the tangent. So in that situation, I can get my R3 is given as 37, my R4 is what I'm searching for, equal to 90. So R4 is simply 90 minus 37. So if I take 90 minus 37, I see my 53. So I get 53. That's my R4. Then lastly, I'm looking for S3. That is where S3 is. So I see S1, S2, S3 are on a straight line. I only know S2. So if I can know S1, then S3 will be easy for me. So looking at it, what I have here, I also pick up that PR is the diameter. So the angle subtended by the diameter at any point on the circumference is a right angle. So that immediately tells me that S1 plus S2 is equal to 90, which are angles in a semicircle, or angles subtended by diameter. So if those two give me 90, and I know that S1, S2, and S3 lie in a straight line, then it's obvious that S3 should also be 90. So if I can just put it down, S1 plus S2 plus S3 is equal to 180 angles in a straight line. Then knowing that this 2 is 90 means you're saying 90 plus S3 is equal to 180, and that immediately tells you that S3 is 90 degrees. So guys, that that was a simple question, so we are done with that one. Let's now have a look at the next question, which looks a little bit long. So we've got another circle with A, B, T, C on the circumference. So the information I picked from there is that AT is the diameter, it's clearly indicated. Then BC is perpendicular to OF. BC, you are here, they are perpendicular to OF. You can see the angle 90 indicated there at F1. Then you see a lot of chords involved. AB is a chord, AC is a chord, BC is a chord. So those are the chords involved. Even BD is a chord. Then A2 is given to us as 30. Then we've got a lot of radii. We've got OA is a radius, OC is a radius, OG is a radius. Just showing to us where we can go for help if we are struggling. So the first part under Roman 1a says we need G, and G means we are looking for this angle. So if I need angle G in that diagram, I think the first thing that will take me there is my diameter, because I know that angle subtended by the diameter should be a right angle. That means I should be able to use my diameter create a triangle anywhere on the circumference. So if I know that this angle B is 90 and I know A2 is 30, then it's easy to get there. So I'll start by saying angle ABD is equal to 90. Those are angles subtended by diameter. So if it is 90, but I know that A2, which was given to me, plus the ABD plus angle G itself is equal to 180. That is sum of interior angles of triangle. Then it will be easy now to get D, because our A2 was given as 30. We have just proven that ABD is 90 plus D equal to 180. Is therefore showing to us that angle D should be the 60 degrees if I take 180 minus 120. So to be on the safe side, I can go there and put 60, because certainly it will help me as I move forward. So that is it. So let's go to the B part, which needs A1. So A1 is up there. So looking at where A1 finds itself, it is inside the triangle. Remember I said here, you can also pick out the triangles involved. So if you are struggling, you can get help from a triangle, and there's even isosceles, since I can see that OA and OC are the same, so I can get help. So to get A1, I see it first of all in a right angled triangle. That is a right angled triangle. So F1 is 90. So if I can get C1 plus C2, then it will be easy to get A1. And how do I get C1 plus C2? It's simple, because our AB is a chord. You can use that option of angles in the same segment. So AB can take us in a triangle to D, and the same AB can take us in a triangle to where there's C1 plus C2 to give me angles in the same segment, which are supposed to be equal. So the whole of this angle there is supposed to be 60, just like angle C, because they are in the same segment with the help of chord AB. So we can describe C1 and C2 as ACB is equal to angle D, which is equal to 60 angles in same segment. So those angles are equal, and therefore, if that is 60, to be on the safe side, let's just go and put it there. Then it will help us see that AFC is a right angled triangle. So we will see that A1 plus F1 plus ACB is equal to 180. us, and we've just calculated this one to be 60 equal to 180, and that immediately tells us that A1 is equal to 30. So this kind of problems, if you are done with the calculation, you don't want to lose what you have done, or you don't want to get confused somewhere, it's good to go and put it there, because certainly it will help you as you move to the next stage. So I've replaced my A1 by 30 degrees. So let's now look at C, which is looking for C1. So you see where C1 is, we can already pick it that C1 plus C2 give us 60 degrees. So if they're asking you to get C1, if you can get C2, you just subtract from 60 degrees. Up to so far, where C2 is, it is inside an isosceles triangle, because you see that OC is a radius, OA is a radius. So by the definition of isosceles triangle, A1 and C2 are supposed to be the same. So I can quickly say, you see, because we put our A1 there, it helps us to see that fast. So I can see that A1 is equal to C2, and that is equal to 30 degrees. So how did I see that? I saw an isosceles triangle COA. So in that way, it will be easy to get C1, because we can already see in the diagram that C1 plus C2 is equal to 60. Since we placed our 60 there, and we've seen our C2 to be 30. So therefore, C1 is just 60 minus 30, which gives us 30 degrees. So that's how simple it is that we got to C1. So we're done with the Roman 1. We can now go to Roman 2, which says prove that AB is a tangent to the circle through BDF. So we've got our BDF. So if you are proving that AB is a tangent, AB is a tangent through BDF, that means you must, to make things easy for you, you have to try to draw a circle, because it should be a tangent to a circle that is passing through BDF. So to make life easy for you, it will be advisable to put a circle passing through BDF. So try to put a circle there, passing through BDF. If you can put a circle there, let's make that circle visible. So if you make a circle visible around BDF, then you see something like that. So in that way, by putting my circle, making it visible, I hope I don't change any information there. So that's what I get. And that immediately helped me to see that BF is a chord. And for this AB to be a tangent, then you start seeing the possibility of a tan chord theorem. So if you can succeed to prove that B2 is the same thing as angle D, because if BF is a chord, then the angle between the tangent and the chord should be equal to the angle in the alternate segment, because if we use this chord BF to create a triangle, you see that triangle goes to F. So if we can succeed to prove that B2 is 60, then we are on the right track of proving using the tan chord theorem. So proving that B2 is 60 looks easy, because we have already proved that BF is perpendicular to OF. So we can see that that angle is 90, and if B1 and B2 are on a straight line, B2 is 90, you see that A3 is 30, then B2 is obvious that it should be 60 in that triangle AFB. So what am I doing? I'm going to say B2 plus, sorry, B2, F1 plus F2 lie on a straight line. F1 plus F2 must give me 180 straight line angles. So in my diagram, I see F1 is 90. So you've got 90 plus F2 is equal to 180, and that immediately shows to you that F2 itself is also angle 90, is the right angle, and we know A2 is 30, therefore B2 is 60. So you can see there that A2 plus F2 plus B2 is equal to 180, that is the sum of angles in a triangle. So our A2 you had 30, that was given. Our F2 we've seen it to be 90, so B2 is what we are looking for. So we've succeeded to prove that B2 is equal to 60 degrees. So if B2 is actually 60 degrees, which is an angle between the line AB and AF and FB. FB is a chord, and this angle is also the same thing as D. And if this is a chord, then if you take that chord as we explained, take us to the circumference of the red circle. So it's like this is the tan chord theorem. They also call it the converse of the tan chord theorem. So if you succeed to prove that B2 is exactly the same as 60, then it therefore tells us that AB is a tangent. So AB is a tangent. Our reason is tan chord. You can also call it the converse of the tan chord, because it's like doing the reverse of the tan chord, because we use the angles to prove the tangent. So that is how it is in the Roman 2, which I know it is not easy for you to understand. We can now go to the last one, Roman 3. It says if it is further given that EC is equal to EA, where is EC? EC is equal to EA. So if it is given that EC is equal to EA, then they indirectly tell you that E is the midpoint of AC. Prove that FCEO is a cyclic quad. So FCEO is a cyclic quad. FCEO. So you see it's a four-sided figure. For it to be a cyclic quad, all we need to prove is that the opposite interior angles sum up to 180. F1 is already 90. So we can prove that E1 is 90. It's down. So E1, we all know that E1 should be 90. And how did we declare that it is 90? Since we are told that EC is equal to AE, therefore the line from the center of a circle through the midpoint is perpendicular to the chord. The line from the center of the circle through the midpoint of the chord is perpendicular to the chord. So that is the theorem we are seeing there. So I'm seeing that line from center through midpoint of chord is perpendicular to chord. So that is the theorem that we have picked there to declare that E1 is also equal to 90. And from here, we can now see that E1 plus F1 is equal to 90 plus 90, which is 180 degrees, and therefore our FCEO is a cyclic quad. So guys, as I said, the second question was a little bit challenging, but I guess I've managed to take you through it. Thank you very much.